begin, if Judy is ready, with the Pledge of Allegiance.
Hold on.
You'd all join in. I pledge allegiance to the flag of the United States of America and to the
republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All right, let's play. I'm Greg, W0QI, and I don't know what order you want to do this in.
Why don't you just call them out?
I can bring them all up here. Judy, if you can bring them all up, you call them out.
How about Al?
Al Van Dyke, WB8RGE.
Jeff?
Jeff, W8GNM. I'm in Northern Ohio.
Welcome. Jack?
Yeah, this is Jack, AB4WS in Big Bone, Kentucky. Good evening, everyone.
Good evening. Mark? KD4, DLU?
Hi all, Mark Washam. I'm in Florence, Kentucky.
Okay. And we'll go to the other Mark, Mark Volstead.
Yes, Mark Volstad, AI4BJ in Burlington, Kentucky.
Okay, David.
I'm David. I'm a KO4BOM, and I'm from Oldham County, Kentucky.
Welcome.
Thank you. Yeah, it's nice to figure something out with this stuff.
The other Dave.
I don't know. I have to turn off the ringer.
I'm Dave Core, KAWDA, Independence, Kentucky. Greetings, everybody.
Thank you. Tommy?
Hey, VJ? Yeah? It's Ron. Hi, how are you?
Okay. Julie?
Yes, this is not really Julie. This is Dan. This is my wife's laptop, and ordinarily I wouldn't touch a Windows machine with a 10-foot pole, but I have to make an exception here. I'm N7QB in Alexandria. Hello, everybody.
That was N7QB?
Yes, ma'am, that's correct.
Okay, thank you. Christian?
Hi, this is Chris, W4ALF in Independence, Kentucky.
Okay. And Ron? We're not hearing you. Okay, so I don't hear Ron. Anybody else hear Ron?
Nope.
No, he's muted.
Okay, WX4.
Okay, now you should hear me.
Okay, there you are.
Sorry about that. WX4GPS, Ron, Georgetown, Kentucky, Scott County. Good evening.
Very good. And Enrique?
Hello, everyone. KO4SR. I'm in Fort Mitchell, Kentucky. I'm doing independent starting Monday. So I'm moving.
Where are you moving to?
Independence.
Oh, outstanding. We're at Independence.
Yeah. Currently in Fort Mitchell, so not too far.
Okay.
Well, you'll like it out here, and on Thursday, they're going to have the party in the park.
Cool.
So, and it's still going on.
Okay.
So it's not going to be hosted by the city. It's by Hand in Hand Realty. It's just going to be music, no food trucks, but you can bring a cooler.
Cool.
Okay, Greg,
All right, as we like to do to our presenters,
Oh, boy.
Jeff, is you have earned your professorship in our Elmer University. And it comes with all the privileges of professorship, and you can refer to yourself as professor, especially up in your local club. And again, we want to thank you for presenting tonight, and hope to have you in the future with some of your other ideas. So thank you.
You're welcome. Thank you for the professorship.
All right. I will ask everybody to pause. We did lose a member between meetings. KI4QG Joe Stern passed away. So a moment of silence, please. All right, thank you. He'll be missed. What an icon of field days.
So anyway, I'll introduce myself. I'm Jeff Mendenhall, W8GNM, coming to you live from Catawba Island, Ohio. My address is Port Clinton, which is the walleye capital of the world. And I live on Catawba Island, which is the first island north of Port Clinton. This is the island you can drive to year-round. And so we have all the luxuries of cable TV and utilities and all that stuff here. So I used to live in Cincinnati. I was there in the Cincinnati area for 17 years and was very active in the GCARA, still co-manager of the 1936 net, which was started in the year 1936. So I co-manage that with Jay, K8CJY, who I know has also presented to you folks. And pleased to have the opportunity to present to you this evening. As I talked to Judy, maybe some other presentations. I have one ready to go on beverage antennas. So if anybody's interested in beverage antennas, we can do that one later. So what I want to talk to you tonight about is the WLW, the historic 500,000 watt transmitter site located in Mason, Ohio, just down the road from the Voice of America Museum, where Jay is also very active. And every other year during the Dayton Hamvention, we typically had a tour. One year we would do the Voice of America Museum. The other year we would do the WLW transmitter site. We were actually supposed to do the WLW site this past May. And of course, with the COVID, that got canceled. But at any rate, the remnants of the old 500 kilowatt transmitter are still there. A couple of years ago, Randy, K7AGE, was in the group that attended one of our tours, and he pulled out a video camera and a couple of wireless mics and mic'd us and said, do your thing. So Jay and I did a video. We didn't know we were going to do a video, so we didn't have a script or anything, but Randy recorded it, did a nice job of editing it. It's out on YouTube. I don't know if any of you have seen it. If you have, forgive me for running it again, but I thought it would be a good idea to run that and just give you an overview tour of the site. And then when the video is over, it runs about 30 minutes. When it's over, I'll come on with a PowerPoint presentation, a few more slides to go into a little bit more depth on some of the technologies that got glossed over in the video. So with that, see if there's any last comments, Judy, before I start the video.
No, I don't think so.
Okay,
Thank you.
I'm going to go ahead and see if this will work, and I'm going to test it, run a little bit, and then stop it. So here we go. I'm going to go to full screen on the video.
A package of Avalon cigarettes, please.
Yes, sir. Oh, just a moment, sir. And don't forget your change. You never guessed, but Avalon cost you less.
So why not always travel on with Good evening, friends. Good evening. This is Del King.
Hello, Randy, K7AGE. I'm at the WLW station. So we're going to take a little tour inside this building, and we're going to kind of go back in time. Back in 1932, this station went from 50,000 watts to 500,000 watts. It was the only AM commercial radio station ever to go to 500,000 watts.
Welcome to WLW. My name is Jay, Kate CJY. This is Jeff, W8GNM. We're both ex full-time Harris people, now part-time Harris people. Ted Ryan, Ted's the chief engineer for WLW. And Ted Kendrick is a retiree from this location.
Station engineers for this facility, yeah.
So a little bit of history. WLW went on the air in 1921. Started out as a 5-watt station in Powell Crosley's living room. The next move was to the factory for Crosley Manufacturing, which originally was a manufacturer of automobile accessories, and went to 50 watts, and then later to 500 watts using homemade transmitters. Ultimately, they went out to a place called Harrison, Ohio, which is far to the west of Cincinnati, with 5 kilowatts. And there was another station that went on the air in around 1922 that was put on the air by the U.S. Playing Card Company. And its call letters were WSAI, Standard Amusement Incorporated, which was the parent for U.S. Playing Card Company. WSAI's purpose when it went on the air was to teach people to play bridge. And they played around with that for a few years and finally got kind of tired of it. And Crosley, sort of in the mode of an LMA, ran it for a while and then ultimately bought it. But while it was owned by the U.S. Playing Card Company, they moved the transmitter from the plant in Norwood out here to this piece of property in Mason, Ohio, built this building over here, which is now where Ted and his wife live, and put a Western Electric 5 kilowatt transmitter in that building. And out here in the lawn and behind it were 2 towers that supported a flat top antenna, with the house kind of right in the center of the flat top antenna. And for 3 years, WLW operated from the site in Harrison, Ohio. And Powell Crosley always did things in 10 dB increments. He always wanted to grow in 10 dB increments. So he was at 5 kilowatts, and the next increment was 50 kilowatts. And he realized he couldn't do it down in Harrison. So he bought WSAI and came out here with WLW by building this building, the front half of this building, and over in the field over here put up a tower and another one in the back, with the white building out there as the center point between those 2 towers, and put another flat top up, and bought a Western Electric Model 7C transmitter, which we're going to see the sort of the pieces of. And actually the building out here is built out of the white building is built out of the packing crates that the transmitter was shipped in. We've actually verified that. We went out, pulled the ceiling tiles down, and the Western Electric stamps are on the wood. Okay? So they installed the 50 kilowatt transmitter out here. WLW was one of the first 50 kilowatt stations, but Powell wasn't satisfied with 50 kilowatts. So that happened in 1928, and he began thinking about the next 10 dB and what it would take. And at the same time, vertical radiators were coming along and people were getting away from flat tops. So he contracted with Blah Knox and built what was originally an 831-foot vertical radiator. It was 831 because there was a mast a lot taller than the one on top that was on the tower. The idea was build an antenna that could handle 500 kilowatts. And they then went to RCA, who was not in the transmitter business at that point in time. RCA was more of a project manager, and RCA took on the job of designing and building the 500 kilowatt amplifier, not a transmitter, but an amplifier, because it was a power supply, a modulator, and an RF deck that was driven off the 50 kilowatt Western Electric transmitter. Contracted for in 1932, delivered in the winter of 33, and first put on the air in the spring of 34. And to do that, they had to build a building essentially around the transmitter components. So they added a rear section to this building, and the transmitter basically takes up from east to west on the building. Most of the magnetics were out back on a pad. There's still part of them out there. The modulation transformers were in the basement, along with filter capacitors, and you'll see pictures, not tonight, but there are pictures around of the original filament and bias supplies, which were large rotary converters, motor generator sets, to develop the thousands of amps of DC necessary to light the tube filaments in the transmitter. So WLW went 500 kilowatts. They were on the air a short period of time, and a grievance was filed by the Canadian government because they were obliterating a station on, I think, on 690 up in Toronto, near Toronto. And Crosley had a lot of smart engineers, so they got together and developed a pair of vertical suppressor towers, which were actively fed by sampling part of the transmission line power, routing it out on open wire, and the two suppressor towers were across the street on property that was also owned by Crosley and known as Everybody's Farm. Everybody's Farm was an experimental farm that Crosley used and actually gave agricultural reports throughout the day, market reports, as well as instructing farmers how to fertilize, how to plow, how to plant, etc. And there was a studio across the way, they put the suppressor towers up over there, and they were able to reduce the signal level in Niagara Falls, New York, at 500 kilowatts to the same level it would have been at 50 kilowatts without the suppressor towers. So that enabled them to continue operation at 500 kilowatts. They went back on the air in the fall of 34 and continued to operate until 1939, but they operated on a special temporary authority, so they didn't have a full-time license. Every 6 months they had to go to Congress and the Federal Radio Commission, and later the FCC, and renew the license, the authority to operate at 500 kilowatts. And eventually they were challenged because they were actually operating with one station and covering as much as the networks were covering with groups of stations all around the country. And many, many entertainers got their start here in Cincinnati. People like Red Skelton, Red Barber, who was a famous sportscaster, a number of other folks performed on WLW from the studios, which at that time were in the Crosley Manufacturing Building down in Spring Grove Avenue.
So you are looking at the remnants of the 500 kilowatt Crosley transmitters. Jay mentioned this transmitter was designed and built in the early 30s, 1932, 1933 era. RCA Victor Corporation was the program manager, and they get to put their name on it and take credit for it. But it was actually built by a team of companies and individuals. The RF power amplifiers, and I'll say more about those. Those are these three cabinets over here. Were designed by engineers from General Electric. The audio section, which is right behind me, the power supply rectifiers are at the far end. This section here, which is the modulator and the transformer and the magnetics, were designed by Westinghouse in Pittsburgh, Pennsylvania. The magnetics were designed and manufactured in Pittsburgh. So it was a joint effort. I did a little bit of research on this a number of years ago and looked at the team members, and I came to the conclusion that the average age of the engineers that developed this transmitter, remember, there's nothing like this has ever been done before. This is really groundbreaking. The average age of these guys, and they were all guys, I'm sorry to say. Today we'd have ladies involved. They were 27 years old, average age. So this transfer was, as I like to say, and Dave Hirschberger will understand this very well, this is designed by a bunch of space cadets, right? Right? So they did have a couple of old salts to help them along the way and guide them and mentor them a little bit, but it was a very young team of engineers. You can imagine how excited these people were to be working on a project like this and really breaking some ground. Jay is leaning on one of the 892, is that the 892 or the subsequent one? That's the three-phase filament one. So 862, but this thing had a lot of water-cooled triodes. This is the water jacket to cool them. Did you point out the cooling pond outside? I don't know if you noticed that thing looks like a vacant or dead swimming pool. Yeah, yeah, that swimming pool out there, that's a cooling pond. They used evaporation cooling to chill the water for the transmitter. There are 4 tubes in each of the 3 amplifiers. Each of these 3 amplifiers could generate about 180 kilowatts of power, and they were seriesed. And then the modulators had more pairs of these 862 or 892 tubes. Now, the original tubes had to have DC on the filaments. If you didn't have DC on the filaments, you'd get modulation in the tube. As the voltage varied across the filament with a 60 cycle rate, it would modulate the emission of the tube and introduce hum and noise on the carrier. So they had to use motor generators. So they had AC motors in the basement driving DC generators. And as Jay said, there were thousands of amperes of DC power being generated to light the filaments.
1500 amp DC motor
Yeah.
generators.
Later on, if you look at this, this is a little more complex. This has 6 pins. They're 3-phase filaments. So there's actually 3 filaments in there, and they were organized so they could put polyphase AC power on them and have humbucking in the filaments themselves, so they didn't have to have DC power to operate the filaments anymore. When you go by here a little later, we're going to walk around in a minute. We're going to go behind the transmitter, and I'm going to open some doors to show you the back of the power amplifier. But you'll see a lot of Pyrex tubing here. There was about 12,000 volts DC on these tubes, so the water that was touching them and flowing over them to cool them had to be distilled water, had to be very pure, and there had to be a long creepage or insulator path in the form of Pyrex tubing or spiral wound ceramics to get the voltage from ground potential up to 12,000 volts and back safely. The power amplifiers, when we look at the construction of them, they were push-pull amplifiers. When you go around back, you'll see the tank circuit. So anyway, let's see, what else can we say?
Just that when this transmitter was on the air, it took a team of engineers watching it all the time.
About 13 engineers.
Yeah.
And the startup process was several hours because they had to bring tubes up to temperature. We have a friend who's 90 years old, Clyde Hangley, who's the former VP of Engineering at APCO Broadcasting. Clyde started here as a co-op student from the University of Cincinnati. And his job on for the startup of the 500, by the way, the 500 ran until 1943
on a temporary basis overnight, only from midnight till 6 in the morning.
During the experimental period.
And
It
it
ran,
was
yeah.
operated under the call W8X7 on WLW. But Clyde's job was to come up and crawl into the individual cabinets, no high voltage, only filaments on, put welding goggles on, and look down into the tubes, individual tubes, to see if anything had moved physically that would cause a filament to grid or a grid to anode short before they started applying high voltage. And he had 12 tubes to cover in the RF deck and another 8 tubes to cover in the modulator. That's part of the startup process.
Starting up this.
How often he found such a problem? I have no idea.
Yeah, actually, he was going to try and be here this evening, but for whatever reason, he didn't make it.
You might want to talk about the switching, because
Yeah.
there are 3 PAs, 2 modulators, and all of this could be isolated. There's a very unique switching system. Jeff?
Yeah. Well, just to finish up with what Jay was saying, starting up this transmitter was a little bit like a shuttle launch. So there's a large crew of people, and there were a lot of steps and checklists and things to bring this transmitter up. So I think what Jay was referring to, and we're going to see some more of these parts as we walk around behind, and then we're going to go down to the basement and see one of the original modulation transformers. But these 3 power amplifiers were actually connected in series, and you'll see a sliding switch that's just under the floor here that could be used to put all of the amplifiers online, or any combination of them online. The coax you saw running out to the tower, that big cylindrical lumen, that's the original 100 ohm coaxial line that was homebrew, basically. 10-inch, it's about 10 inches in diameter. They use heliacs now, 3-inch heliacs for the 50 kilowatt. There were 2 modulators. There were 2 separate modulation transformers, so they were completely independent. And they could route those, they could run them in parallel, or they could route them individually to a single amplifier or pairs of amplifiers. The modulator was capable of about 180 kilowatts of RMS power per modulator, yeah. So it'd be 360. So it takes roughly 50% of the carrier power to 100% modulate transmitter. So
I recently read an article on when they were bringing the transmitter up and the testing they did. And according to the article, at one point in time in the testing, they actually had the thing up to 800 kilowatts carrier. So there was a lot of over-design.
Just to give you a order of magnitude here, this is driven, the driver is a 50 kilowatt transmitter in the next room, the Western Electric. So, this is on 1 amplifier. This is the grid amp meter. So it goes to 10 amperes of grid current, right? And this is an RF amp meter. Notice it's a nonlinear scale. So this is a thermocouple, General Electric RF amp meter. This is the plate tank circuit amp meter. It's 160 amperes full scale for 1 amplifier, right?
The power supply, 12 kilovolts, shows that the power supply can operate at 100 amps. So 1.2 megawatts of DC.
So those are the 3 RF power amplifiers. These are the modulator sockets. So for each of the modulators had 4 tubes in parallel push-pull. And you can see the tubes are still in the water jackets here. This is another one. I think the tubes have been removed. Now there's 3 tubes left. 2 of them are still in the sockets, and the 3rd one there. Here's a piece of the Pyrex pipe. Piece that got broken, but you'll see a lot of it. You see a lot of other Pyrex fittings here that were used to carry the distilled water in and out of the tubes. Now, the original rectifiers were glass mercury vapor rectifiers. They were later replaced with metal mercury vapor rectifiers, but you can still see them here. So this is a polyphase 3-phase rectifier with 6 rectifier elements in it, okay? So these are actually mercury vapor rectifier tubes that were used to rectify the high voltage AC to DC. The filter capacitor banks were in the basement, and you'll see those in a little bit. This is the Faraday shield here. You can see the rods that are all connected back to ground and open circuited at this end. This inductor back here, my hand is, that is the plate inductor. This piece here, you see this piece that rotates? That's the variometer. It can rotate all the way around in the other direction. So this is what's used to tune the amplifier. You can see the two, what we call bread rack assemblies. These are the, again, if I had a, should have brought a flashlight with me, but yeah, there you go. Great. All right, so thank you. So here you can see, this is one of the bread racks. You can see the alternating plates. So it's just like an fixed air capacitor. And the other one is over here. And the two top sections here are then connected to the two pairs of tubes. That's one of the plate chokes to get the DC onto the lines here. You can see all the attention to detail on the corona rings here for high voltages. This push rod here moves this section. This is the output coupling inductor. This moves back and forth, so it comes out this direction or moves back in closer to change the output loading of the transmitter. And the output from the transmitter are these two 3/4 inch copper pipes that go down into the switching mechanism underneath the floor there.
And how is the variometer tuned?
From the front panel, see this gearbox here? Yeah, so you just dip the plate current, and peak the output, and you see the flexible couplings here and the gearbox, and see the insulated section here, okay? Corona ring there, and this is a rotary joint. So this one turn that I'm shining the light on right here is the one that turns, and there's a sliding contact, a rotary joint right there, and another one at the top. So we've actually disconnected these things and measured their inductance and measured the inductance ratio because we wanted to learn about, we were trying to build a 250 kilowatt variometer for a modern transmitter and trying to learn about how this one worked.
So this is the part of the building that was added on when the 500 kilowatt was built. And there's, again, remnants of the 500 down here. When the 500 was built, there was a substation that was built out on Towersville Road. Right now, there's nothing left but the weather heads where the cables come out of the ground. There were huge transformers, disconnect circuit breakers, and two feeds. One came from the Port Union substation, the other came from the Oakley substation and came up, and they could select power from either of the two substations, the feeds into the plant. 33 kilovolts primary power, stepped down to 2400 volts, and the 2400 volts, and there were dual feeders, came into the building right here on cable A and cable B, and from there, the power was routed over here to these oil breakers, which had the ability to cut the power in literally a cycle or two of the AC sine wave. And that then fed AC back out to the plate transformers, which were on the pad behind the building. So there are a number of breakers, and then there's control power over here, which was used to feed the control circuits of the transmitter. And this back part of the room was all filled with the rotary converters. Later on, the rotary converters were transferred over to filament transformers and power supplies, which were on a pair of I-beams that spanned the building. And the holes that you see in the ceiling were where the filament wires went up to the tube sockets. And that was all torn out sometime, I guess, in the 70s or 80s. So anyway, there's also a harmonics filter and changeover back here, which you can take a look at. And then the switching system that Jeff talked about is
this large ductwork that runs underneath the amplifiers. And all of that contained the high voltage, the RF, and other control circuits that were part of isolating each of the amplifiers.
So while we're standing here, this is one of the two modulation transformers. So it doesn't look like exactly like what we hams think of a modulation transformer being some laminated transformer. It's a big tank of oil with the transformer immersed in it, so it's like a giant pole pig. I'll read you the specifications here from this. Okay, so this was built by Westinghouse Electric in Pittsburgh. It's 180 kilovolt ampere capability, operated at 6,365 volts. It's rated from 30 cycles to 10,000 cycles audio frequency response. It has 725 gallons of oil in it. So the weight, approximate weight of the transformer itself, the magnetics of this one by itself is 27,000 pounds of steel, iron in it. The case is 3,250 pounds. The oil is 5,460 pounds. Its total weight is 35,700 pounds for this, okay? The high voltage input was rated up to 14,400 volts. So this was one of two modulation transformers. I often wonder what it would have been like to stand beside one of these while it was modulating, whether you'd hear anything. You know, we're used to hearing a non-oil immersed transformer kind of talk, the magnetostriction of the laminations pulling them, being squeezed together and expanded as the current goes through the transformer. So you kind of hear audio coming up. I don't know whether this is all muted or glug, glug, glug and oil, but it would have been interesting to stand beside this thing when it was putting out 180,000 watts RMS audio power. That is a big audio amplifier. And there were two of them here. The other one was standing right beside it. So pretty impressive. The modulation reactor was out on the back pad. So the audio from this transformer was AC coupled to the power amplifier, and the DC feed to the amplifier was through another device almost as big as this called a modulation reactor, which was just a large high inductance choke that was used to feed the DC to the power amplifier tubes and offered a high reactance to the audio so the audio could go across it. But they didn't want to put DC through the secondary of this transformer because it would saturate it. It would compromise the performance of it. So, yeah.
One other thing I can point out, if you notice over here, what looks like a footer is actually a platform. And when the 500 was there were banks of Pyranol, GE Pyranol capacitors that made up the filter for the 12,000 volt power supply. And there was a series of caps that were used to isolate the DC, block the DC off the winding on the secondary of the windings off the secondary of the two transformers. So the coupling cap for the audio and the filter caps for the power supply were all out in the open. You can imagine having something like this today in the world of OSHA. Yeah. Right?
Well, this room was interlocked. It had to be interlocked. You know, it would be a death chamber. This is a bank of air capacitors, and I believe this was originally out at the antenna tuning unit. Okay, so these are cylindrical coaxial air capacitors. Okay, so they're just air gap space and they're in parallel. So there's 6 of them in parallel to form a high voltage capacitor. And there's also a lighting choke here for AC, decoupling the AC lighting from the tower. There's what's called an Austin ring transformer out there now. The part of the original harmonic filters over here, so you can take a look at the stack of capacitors they have. These are mica capacitors that are in series and in parallel to form one of the capacitive elements in the harmonic filter. And here's an antenna line switch. It says it's a switch between 50 kilowatts and 500 kilowatts. So it must have been between the two transmitters. So
This originally sat over there, right underneath that.
okay.
Coax.
Okay. So if you look up here, this is the coaxial switching arrangement. And this is beneath the power amplifiers. So you see there are 3 different transmission lines from 3 different amplifiers here that had a sliding switching arrangement so they could connect them in series or take some of them offline and leave the others online. So, and then the output line to the antenna system was right here. So this is the RF switching network, all homebrew, as we should say, you know.
Friends, we cordially invite Saturday evening at the same time when the Brown and Williamson Tobacco Corporation will again present Avalon Time. This is Del King saying good night, everybody. Avalon Time originated in the studios of the Nation Station and has reached you through the National Broadcasting Company.
Okay, hope that came through all right. And we're going to switch here.
Yes, we do.
Okay, perfect. All right, thanks. Well, I hope the video came through okay. And I thought I would just run a few more slides here to dive in a little deeper on some of the technology that you just saw. So first of all, you saw a brief glimpse of the coverage map when Jay was talking about the interference problem with the Toronto area. And after the suppressor towers were put in, this is what the coverage looked like. You can see the little see if my mouse will go up in there. Yeah, you can see the little dent in the pattern that the suppressor towers put in. But if you look at these contours, this is like 5 millivolts, 5,000 microvolts per meter through all the way through central Illinois, all of Indiana, Ohio, most of Michigan. Then you go out to 2 millivolts per meter, 2,000 microvolts per meter. And, you know, we're out in Kansas. So this, you know, all the way down into northern Florida. So this is, you know, this is still considered city grade coverage. Okay. And then the half millivolt or 500 microvolt per meter contour, you know, went out through Colorado, parts of New Mexico, and through a lot of Canada. So you can see what amazing coverage this station had at 500 kilowatt power level. So, you know, as Jay was talking about, Crosley thought in 10 dB increments, and the tower that they used for the 500 kilowatt was a very novel design, moving away from a flat top radiator and going not to a quarter wavelength vertical, but a half wavelength vertical, actually slightly more than half wavelength. And so they selected the height that would yield about a 3 dB gain over a conventional antenna. They also had a problem with the voltages on the guy wires, and you may recall when you saw the picture of the diamond-shaped Blau-Knox tower that it's only guyed at one spot in the middle. And there's a reason for that. Being a half-wave tower, the voltages are high at the base insulator and at the top, but the voltage is at a minimum about halfway up the tower. So where the guys were attached to the tower is where the voltage was a minimum, and also the current, the RF current, was at a maximum about halfway up the tower, where the cross section of the tower was huge. It was 30 feet 30 feet across each face of the tower. So the antenna had very good voltage and current distribution on it and a very good bandwidth. So Blau-Knox of Pittsburgh developed this tower. Blau-Knox built a lot of bridges and other similar structures, but they came up with this unique design. And it's only guyed at one level. If you think about it, the diamond-shaped tower is actually made from two self-supporting towers that are stacked with the bottoms tied together. So the bottom tower is inverted, and the top tower is self-supporting from the center point where the guys are. Here's a picture of setting the base insulator for the 831-foot antenna. And this base insulator had to withstand a compression force of 450 tons, which included the weight of the structure plus the additional downward pressure produced by the guy wires. And here's a recent picture of it to show you, you can see where the guy is attached. This is 30 feet across. And there are 8 sets of guy wires. They do have insulators in them to break them up, break up the resonances. But structurally, it's an amazing antenna system. Okay, so as I said, it was built in Pittsburgh, designed and constructed there. Base was set in 1933. It was completed in only 3 months. $50,000 in 1933 dollars. I haven't extrapolated what that would be today. And it was 700. The basic tower structure was a little over 700 feet, with the guys at 350 feet, and then there was an additional mast that took the total height to 831 feet. So it was somewhat over half wavelength, close to 5/8, and that mast could be raised and lowered. They experimented with changing the height of this tower to try and mitigate fading right around sunset, when you had simultaneous ground wave and sky wave, and there was an interference ring around the antenna system that was over around Indianapolis, Indiana, and they were trying to adjust the takeoff angle of the antenna to push that interference ring out further, so that it didn't affect the close in or local coverage as much. The antenna had, being a series fed with a base insulator, had to have lightning chokes, some way of discharging the static electricity, and it also had ball gaps that were used if the ball gap spacing had to be adjusted so that it wouldn't flash over with normal modulation, but if it got hit by lightning, it could dissipate the charge. And you see this device in the background that looks like a gun barrel. That was actually a photo detector that looked through the ball gap. And if there was a lightning strike that caused the ball gap to fire, and then there was an RF arc sustained from the 500 kilowatt transmitter, this would detect it and shut the transmitter off momentarily to clear the arc, and then restart the transmitter. As you saw a little earlier, the coaxial line was homebrew. The impedance was 100 ohms. It was about 800 feet long. And they constructed it out of 10-inch aluminum irrigation pipe with a 2-inch diameter copper pipe interconductor. The amazing thing about this line is it was not pressurized. It had slip joints that were slip fit with hose bands, and the inner line was supported by some steatite insulators, but it was unpressurized, which is amazing that it didn't have more problems than it did with condensation and or rainwater or something else getting into it and causing it to fail. And that's what it looked like. Transmission line, then there's conduits on either side for electrical lighting circuits. So you have to remember, again, that no 500 kilowatt transmitter had ever been built at this time. And so, you know, the Crosley engineers had some ideas about how it could be done. And as Jay mentioned, RCA became the contracted project manager, and they subcontracted the Westinghouse and General Electric and several others. So the AF amplifiers, modulators, the transformers, filament supplies, pumps, heat exchangers, all those things were Westinghouse. GE did all the RF power amps, the DC power supplies, high voltage rectifiers, and all the RF components, harmonic filters, transmission line, antenna coupling unit. And it was built largely by a design team consisting of 27-year-old space cadets. Those guys must have had a ball. The original contract amount was $450,000 at 1933 dollars. And the transmitter billing had to be expanded. These power amplifier units were actually built, some of those cabinets were built out of wood framing, and then the framing was covered with metal, copper or tin plated metal, and then soldered. All the seams were soldered. So they had a structure, some of which was wood, and then they just built the transmitter in. It was almost like building a house with a complete shield room around the amplifier. Here's the plaque. This plaque is now at the Voice of America. It's in the Gray Wireless Museum at the VOA Museum in Mason. And another nice photo of the power amplifiers over here, the 3 power amplifiers on the left, and then the audio amplifiers down on the right-hand end. And here you can see, as you saw in the video, underneath this catwalk are the Pyrex pipes that were used to decouple the high voltage from the water. By the way, the water that flowed through those tube jackets had to be highly distilled so that it was not conductive, because it had 13,000 volts across it. And that water then flowed into what's called a brazed plate heat exchanger, a liquid to liquid heat exchanger. The water that went out to the cooling pond was more or less tap water. So it was not deionized water. So they had a series of pumps that circulated the water out to the cooling pond and back to keep this brazed plate heat exchanger cool. And then the other side of that brazed plate heat exchanger was thermally linked, was where the distilled water was flowing. This is what the main transmitter console looked like back in those days. So you saw a glimpse of this in the video. This part of the schematic diagram is actually the Western Electric 50 kilowatt transmitter, which they called the exciter. Faraday shield, and then coupling into 3 identical power amplifiers, each one of them having 4 of the 862 or later 892 tubes. The 892 tubes were the 3-phase tubes. So here are the 3 amplifiers. You can see the outputs are connected in series, and then goes through the harmonic filter out to the antenna. The audio amplifier, though, was part of the 500 kilowatt system. It was not the audio amplifier from the 50 kilowatt exciter. And it had 8 of the 862 tubes in parallel push-pull. And you can see the two 180 kilowatt modulation transformers here. And this device here is called the modulation reactor. So the DC feed to the power amplifiers went through this modulation reactor, but there was no DC on the modulation transformers. You can see the blocking capacitor here, that little symbol. Of course, that was a whole bank of oil-filled capacitors to provide that function. A couple of pictures of the spec sheets on the original 862 triodes. This is built by a company that doesn't even exist anymore, Federal Power Triode. This was long before RCA and IMAC and some of those other companies got into the high power vacuum tube business. And this is the plate of the tube, the anode. It's basically a copper jacket. So this is immersed in water, and it's just basically a sealed copper pipe. The grid connector is here. It is a triode, so there's only 3 elements. So this goes into the grid, which goes down through the tube, and the filaments inside the grid structure. So the filament voltage was 33 volts at 207 amperes per tube. So when you added up all the tubes, I think it was around I think you saw in the videos, around 4,500 amps of DC that was used to light up all of those tubes. And then some of the typical operating conditions was, they have both audio frequency and plate modulated RF power amplifier. So the output from each of these tubes was around 45 kilowatts each. So you got four tubes in each of the power amplifiers, 2 tubes parallel push-pull. So 45 and 45 on one side, 90, and another 90 on the other side. So about 180 kilowatts per amplifier. And later on, in order to eliminate the need for the DC filament voltage, they came up with this novel approach of a spiral wound filament that was actually 3 filaments that were wound in such a way that the electrical field from the 3 separate filaments would cancel when they were fed 120 degrees apart each. So it was a polyphase, 3-phase AC filament system that was designed to buck out the hum that they would have had had they had put AC on the original single-ended filament. Just to explain that a little bit, excuse me, when you think of a triode, the filament emits electrons, and then there's the grid that controls the flow of electrons across to the plate. Well, when you have a filament that one end of it is connected to one end of an AC supply, and the other end, the top end, the bottom is connected to the other side of an AC power transformer, you can see that the voltage, the instantaneous voltage difference between the filament and the plate and the grid is changing along the length of that filament. And that's why you have to have some type of humbucking arrangement. Otherwise, the density of the electrons in the tube is moving up and down the tube, the length of the plate all the time as it follows the AC waveform on the filament. They, as Jay mentioned, they often use welding glasses to look at these tubes in the water jackets before they fired it up. Another picture of the RF PA tubes in their water jackets. So the Pyrex pipe there was a lot of length to this. I don't know why it took quite that much length, but they had to have a voltage gradient, you know, so many volts per inch. They had 13,000 volts on one end, and the other end is a ground potential. So they had a lot of a zigzag labyrinth of these Pyrex pipes to decouple the water from the high voltage. And there's the spray pond. This is the tap water side of the cooling loop. An inner loop and an outer loop. Again, magnitude 10 amps of grid current. We don't even, with our ham rigs, we don't even come close to 10 amps of plate current. And 160 amps of circulating RF current in the tank circuit. Now, one of my favorite parts of this transmitter, as you might imagine, is this output network and this Faraday shield. I remember as a young ham, when I was home brewing equipment, learning about Faraday shields. Why did you need one? Especially when you use inductive coupling from instead of a pi network. Oftentimes in those days we had either single-ended or push-pull amplifiers, and there was a tuned tank circuit, and then there was some kind of a link coupling to the antenna. And what you want to do is prevent the transfer of harmonics from the amplifier into the antenna system due to capacitive coupling between those. So this Faraday shield you see here is a perfect example of how those things work. This thing is a curtain of metal rods, and they're all tied to the chassis ground at the top. They're all insulated at the bottom. They have to be insulated because if they became a shorted turn in between these two inductors, they would have a lot of RF current flowing on them. But the whole idea here is just to screen the capacitive coupling between the plate circuit, what we call the tank circuit, in the background here, and this is the link coupling out to the antenna. There was also a variometer that was discussed earlier. That's this turn here that rotates 180 degrees and either adds to the inductance or subtracts from the inductance of the plate tank circuit. And that's how they tuned this amplifier. The capacitors were fixed air capacitors, what we called the bread racks. And so, and then the Faraday shield was between the two coils to prevent capacitive coupling. And this whole assembly here, this whole rack moved in and out to adjust the coupling or loading. If you're thinking of a ham amplifier, you have plate tuning, that was this variometer, and the loading was moving this pancake coil in and out to adjust the magnetic coupling between the two. There's a picture of one of the two bread racks. These were all homebrew. They were made out of aluminum tubing, and presumably they were made this way so that if there was any debris, like insects or something that got in there, that they would fall through. So these are parallel aluminum tubes that are flattened on the end and tied to a piece of right angle aluminum, and then the intervening plate with the tubes ran the opposite direction, 90 degrees. Very clever. This thing was all put together, you know, with looked like speed rail. They had to put some insulated sections in there, but it was all put together with U-clamps, and I presume all this stuff was, a lot of this stuff was built on site. Some of it may have been prepared in a factory and shipped in pieces, but this definitely looks like a homebrew transmitter. Just a big one. Excuse me. Here you can see the bread racks from the front. And these ceramic devices here have nichrome wire wound on them. These are actually parasitic suppressor resistors. So there's one on each side in this push-pull circuit, and then this is the high voltage feed coming in here. Hal Crosley and a young lady standing down there by those transformers. I don't know whether they were talking at the, whether they were rocking at the time or not, but you know, publicity photo, pretty impressive audio amplifier. And we already kind of went through the specs with the video, but you know, 180,000 watts each. And yeah, pretty good audio frequency, 30 to 10,000. The transmitter would actually modulate 100% from 30 cycles, or as we say today, 30 hertz to 10,000 hertz. That's way better than what most AM stations today cut off their audio at 5 kilohertz. You know, to well, the car radios are so narrow it'd be a waste of energy to go beyond that. But this thing was pretty high fidelity. If you had a, you know, one of those wideband AM receivers in those days, you get pretty good fidelity out of the system. 35,700 pounds all told for each transformer. Now, here's what's on the air WLW today. This is one of two Harris solid state 3DX 50 kilowatt transmitters. Actually, Harris makes transmitters based on this same digitally modulated technology that go all the way up to 2 megawatts. Nobody in the United States needs one of those or is allowed to operate one, but there are, the Voice of America has several of them, and a number of Middle Eastern countries have Harris solid state transmitters that operate at power levels up to 2 million watts. And these transmitters are made out of a lot of individual modules that are around 3.5 kilowatts. In this 50 kilowatt one, it's about 3.5 kilowatts per module. And there are 64 of them, and they are turned on and off instantaneously to directly synthesize the AM waveform. So there is, if you think about it, there is no modulator in this transmitter. There's no audio modulator. The audio is digitized, so it's like a big computer. The audio is digitized, and then the correct number of modules are turned on at any instant in time to take the power all the way up to more than 4 times 50 kilowatts, because it'll modulate well over 100%. So it could go, you know, when all the modules are turned on, the transmitter is capable of about 250 kilowatts of peak power. And then when they're all turned off, it goes to 0. It'd be minus 100% modulation. So that's what's there today. So anyway, getting late, so I think we'll stop and go for some questions. So I guess I can stop the share and everybody can turn on their mics. Maybe I can hear everybody and still leave this up if I need to go back to a slide to answer a question. What do you think, Judy?
Yep, it sounds like it's fine.
Anybody have any questions while I have the slides up? I'm sorry I didn't get your logo. I still have the Orange County Amateur Radio Club logo up there, but they're up in New York State.
Okay.
Anyway, any questions? I guess not. Okay.
Well, I do have a question.
Okay.
The oil that was used in the modulation transformers and other magnetics. I'm assuming it was all PCB based.
Yes.
So I imagine they had quite a remediation issue at some point in time.
They have removed it all, except for that one remaining transformer. And that one remaining transformer has a certain number of parts per million of PCB in it. Why they didn't remove all the oil from it, I don't know. They removed all the other capacitors. Actually, there are some capacitors there for the Western Electric 50 kilowatt transmitter until recently was operational. What was the driver for the 500? It's a 50 kilowatt transmitter. And I remember Paul Jellison, the chief there, at the time at the Millennium in 2000, he put the old Western Electric on the air at midnight for a few hours. Since then, they had a problem with some of the Pyrex piping getting broken, so it's not operational anymore. But I know the capacitors are still there. They're all marked, so they all have to be marked as being having PCBs in them. But most of the PCBs have been removed from the site. I guess eventually they'll have to take the rest of it out. From a remediation standpoint, I don't think there's been any kind of a spill in the building, so it would just be a matter of removing the oil and removing the transformers and capacitors, and sending them to the incinerator, I guess.
Thank you.
Jeff, from the committee meetings to the final installation of the aircraft light on the top, how long did this thing take?
Okay, you're talking about the construction of the tower?
Everything.
Everything. I'm going to be guessing at that. Jay's probably a better historian on those numbers. I don't know if he knows the exact dates, but I would say about 2.5 to 3 years for everything. But the tower itself was much faster than that.
Wonder how many years that would take today.
I don't know. You know, the other thing you'd have to ask you, it's a good question, is how much design work was done at GE and Westinghouse prior to coming on site, you know? So how much of it was done on site and how much was done off site?
And you had nothing to fall back on. You were doing it from scratch.
Right. They did have the 50 kilowatt transmitter to stay on the air with, but you know, they did a flash cut. They came up with a switching system where they could sign off, I guess, at midnight with the 50 kilowatt and then go into test mode with the 500 for some period of time. So.
And Jeff, that was Gary. He's our trombonist conductor.
Oh, yeah. Okay. Well, I know Gary. So, yeah. Well, yeah. So, Gary, which bands or symphonies do you play with?
You're on mute.
You're muted, Gary.
There we go.
Yeah.
Well, right now, as a retiree, I'm with the Cincinnati Community Orchestra, and I conduct a brass choir called the Brass Fellowship.
Okay. Okay. My wife's involved with the Fireland Symphony Orchestra.
Terrific.
That's a regional orchestra that in Sandusky. The conductor's Carl Topolo from the Cleveland Pops. But there's another group that I'm also involved with another organization here called the Musical Arts Series Port Clinton, and we bring we have a much smaller venue, and we bring smaller groups in for performances. And have you heard of the Burning River Brass?
I have.
Yeah, they're a group. They all originally came out of I think Cleveland Institute, most of them, but they live all over the country now, and they get together every year around Christmas time, There's 16 members, and we have them here in Port Clinton every year around Christmas. Although we don't know how we're going to do it this year, but the last couple of years we've had them here.
That's really cool. I like the way they got their name too.
Yeah.
I guess it doesn't burn anymore, but that's still pretty cool.
Well, remember the Cuyahoga River? Cuyahoga River was on fire back then. Okay, cool.
All right. Anybody else have any questions?
I have one quick question. When was all this started to be dismantled? This was like booming in 1934 and whatever. When it started to be dismantled?
Oh, okay. That's an interesting thing. I don't think Jake covered that in the video, but this station was a fabulous station for a few years, from 1934 until 1939, but they never actually got it fully licensed. And what happened is there was a Senator Wheeler out in, I think it was Idaho, South Dakota or Idaho, one of those western states, had a constituent that owned a broadcast station and wanted to operate on or about that frequency. Wheeler was a very powerful politician, and basically it was an act of Congress that said Powell Crosley couldn't run at 500 kilowatts anymore. So they shut him down, and he had to go back to 50 kilowatts was the maximum. And for years, they fought this legally, all the way from, this was in 1939, well past World War II. And they operated the transmitter during the experimental period, like from, I think it was like midnight to 2 a.m. for quite some time. In fact, Clyde Hanley, a good friend of Jay's and mine, recently passed away, but Clyde was like one of the last guys that operated that transmitter. He worked for, actually, Crosley lost interest in the station after a while. If he couldn't have 500 kilowatts, he just wasn't interested. And he sold it to AFCO. And then that was subsequently sold to J-Core, and now, it's Clear Channel, now it's iHeart. Changed several times. But at any rate, that's the reason that they had to cease full-time operation in 1939, was because of a powerful senator that convinced the FCC. Actually, I guess there was a vote in Congress that said the maximum power was going to be 50 kilowatts, and so they never got licensed.
Thank you.
Do you have any information on the, it used to be said that 700 WLW was the nation station, Clear Channel Voice, and that it was, there was a system set up for the president to be able to use those stations in national emergency. Any validity to that?
Yes, there was, because of their coverage. And there was also there was some very narrow bandwidth phase modulation put on the carrier of that station. They were testing it as a way of having, we'll call it a long-range teletype type service. So that was experimented with, and of course Hitler could hear the station, and he called it the Cincinnati Liars. So now, let's see, it was, let's see, which president was it? Was it FDR? Yeah, I guess it was FDR that, threw the switch, right, figuratively, remotely, he threw a switch to put it on the air in 1934.
That's good stuff.
Yeah.
All right, anybody else have anything? Thank you, Jeff. We appreciate it.
You're
we
welcome.
Will use you again.
Well, you can use me as much as you want. I'd love to do a presentation on beverage antennas.
Okay, Judy will set that up with you.
Yeah.
Thank you, Professor Jeff.
I don't know about
call all your
professors.
friends, tell them you're a professor now, and
okay.
And
right.
if everybody wants to stand by, we're going to do a brief business meeting and a brief discussion on field day. Radio.